All right, everyone, it's time for the integral unit test. So what we're going to have here is some reverse power rules. I guess remember that this section of integration could probably comprise a lot of the AP exam, just because usually AP tries to center on things you've done more recently, and also integration, in a way, tests your knowledge of derivatives at the same time. So this is definitely an area that you want to focus on as you study. The idea is for the first term, when you underive it, it's going to go back to x to the sixth, and then what you need to think about is when this 6 dropped down, all you were left with was 9. So how do you multiply 6 to something and only end up with 9? Well, you had to have 9 over 6, which will reduce in our final answer. Up next, again, for the next term, when you underive it, the x will go back to the third power. The question is, what dropped down so that there was a 3 out front? Well, 3. And actually, I guess, because you dropped 3 down, and 3 is what's there, you actually don't need anything, you just need 1, and keep the sign negative. And then you have a 7, and that comes from 7x, and don't forget your plus c. 3 over 2, x to the 6th, to the 6th, come on, minus x cubed plus 7x, and just remember to write the plus c in on your own. All right, up next. So the idea is we need to find the area of f from 7 to 3, and so this is one of our what we call algebraic rules of integration, or algebraic properties. And so if we had 3 to 7 of f of x, if we just look at the graph there, that answer is negative 3. But if you decide to flip the bounds of integration, sorry, let me write this as a rule. If you want to find 7 over 3 f of x, not 7 over 3, you know what I'm saying, then this is equivalent to the integral of the original bounds, or the bounds from least to greatest order, but with a negative out front. So what that really means is we need to negate the answer of the original integral, so our answer is actually just going to be positive 3. All right, U substitution already. So when you take a look at this, what I notice, or what makes me say U substitution, is there's no way to break down that fraction. And likewise, we should remember that e to the x, when derived, is e to the x. So I see something that is larger or involves more terms, and that's actually the denominator. So I'm going to let that be u. And then when I derive u, I'm going to end up with, well, this will go to 0, this will be just e to the x, and then I'll have dx. And so the idea is this u, 1 plus e to the x, is all in the denominator. So now I'm just going to write that whole denominator as u. And the numerator really is e to the x times dx. That dx is technically going to the numerator, so we just have du all right here. From there, a common thing you might do is actually change the values. You can, in other words, keep this in terms of u, and we'll change the bounds of integration. So the old bound, the old lower bound, was ln of 2. If we plug ln of 2 into this structure to solve for what that value would be for u, when you plug ln of 2 in here, you'll have e to the ln2, and that will cancel to just give you 2, and then you have that 1 out front, so this will be 3. And then same idea when you plug in ln8 for the upper bound, that's just going to be 8 plus 1 is 9. All right, from there, now we have our integral fully in terms of u. The bounds are now in terms of u, and we have du and u. And the question is, what is this going to integrate to? And when you have a derivative over an original expression, then what you end up deriving to is ln of absolute value of the original expression. And this time I don't need a plus c because this is a definite integral. I'm evaluating this from 3 to 9. All right, when I do that, I'm going to end up with ln of absolute value of 9, but that's just 9, minus ln of absolute value of 3, but that's just 3. And here's one more trick going on here. Ln of 9 minus ln of 3 is the same as ln of 9 over 3, which would just be ln of 3. All right, we have another definite integral question here. I'm going to show you the big trick here. If you notice, this shape is actually symmetrical about the origin is what we would call it. You can kind of see that these look almost identical. There's some kind of weird symmetry going on here. And here's the symmetry going on. If you just take this piece on the left and you flip it either vertically or horizontally first, so imagine I took this piece and I flipped it downward, and then imagine that I took this piece and I flipped it over this line that I'm covering up, you'd have that exact match. When that happens, if you want to think about it like this, there's as much area above the x-axis on this side as there is below on this side. So you have the positive value and the negative value, and we're combining them, and that will just combine to 0. All right. Up next, we're supposed to approximate with Riemann sums and figure out which one is going to overestimate, underestimate, and actually be closest to the actual area under the curve. Or not really actually, but where do all those fit from least to greatest? If we're doing a left-hand Riemann sum, again, that means we're starting at the left and carrying that value over. And you do that here for any point, and you're going to end up always being underneath. So the left-hand Riemann sum is always going to fall below or underestimate. The right-hand Riemann sum, if you start on the right and you carry that value over, well, then that's just going to always be above or overestimate. So left hand will underestimate, right Riemann sum will overestimate, and somewhere in between is the actual area under the curve. All right, up next, this is a common question you would see on the AP exam, so this is definitely one you want to take note of. They want you to integrate this from 0 to 2. The idea is you don't know what function this is, but usually on the AP exam, what they would tell you is from -2 to +2, you're looking at a semicircle. And so because of that, we don't treat this as a function integral, we treat this as geometric area. So we have a radius of 2 of a quarter circle, so I need a quarter of pi r squared, where the radius r is 2. And that's just actually going to give you pi. And it's positive pi because we're looking for something above the x-axis. All right, up next, this is just an application of summation notation. You're actually not going to see anything like this in the AP exam, but they're just trying to help you understand how summation notation works. The idea is you're always replacing I with that value. So for the first one, you would actually just be replacing the I in the numerator, so now you have 7 over 4n minus 9. The next term would be 14 when you plug in 2 over 4n minus 9 plus 21 over 4n minus 9 plus 28 over 4n minus 9. You're just replacing I with the starting value and every integer in between until you get to the highest value. Next, another, I guess what I would call basic integral question, but that exponent is going to make things a little bit tricky. Things that you want to bear in mind, though, is just remember that in your integral, you don't have to think about -6 being in your integral. If it's multiplying to the rest of the function, you can just toss it outside and just worry about the root of x, which we're going to think of as x to the 1/2. All right, now your first step in integrating, I guess we'll keep the -6 along, but we always add the power back. So if I add 1 back to 1/2, I'll get 3/2. And now the question is, how do you drop 3/2 down and you only see -6? Or in other words, how do you drop 3/2 down and make that 3/2 not show up so that -6 is all that's left over? And the short answer is you apply the reciprocal to it as well. Now when I drop 3/2 down, you'll just have the 3's cancel, the 2's cancel, and you'll just be left with the -6, which is what we want. And again, we have to evaluate this at 0 and 25. All right, so I'm still going to keep the -6 on the outside. Actually, what I'm going to do is I'm going to multiply these two together. That's actually going to get you -4. And now I'm going to just plug in the 25. Remember, it goes top plugged in minus bottom plugged in, or b minus a if you're thinking about the complete formula. All right, so now I have -4. And when you raise something to the 3/2, you first want to root the value and then cube the value. All right, the denominator is what you're rooting by, and the numerator is what you're raising to. And you can do that in either order, but always make things smaller before you make them bigger, because the cube of 25 is going to be a very large number, but the square root of 25 is just 5. And then if you cube 5 afterwards, that's 125. And whatever you raise 0 to, it's 0. So it looks like our answer is negative 600. Oh no, what have I done? I'm sure you've been staring at the mistake forever. Oh, because it's negative 500. Be careful with your multiplying. All right. Up next, this is just a basic power rule question, so I'm not going to write it out. Again, what I've been saying is first increase the power by 1, and then figure out how you drop that down, and you don't see a coefficient. And the answer is you need the reciprocal of 5, which is 1/5. All right, same idea again, actually. Just make sure you think about this as the integral of x to the 4/3 before you start integrating this. And again, that means you're going to have to increase the power by 1, so add 1 to 4/3, which is 7/3. Here's a trick for this question. Put parentheses in here and then write the fraction, or just press the fraction button first so that you can write that 7/3 and that 3 doesn't keep dropping down. Now I have the 7/3, and again, when you drop the 7/3 down, you end up having a coefficient of 1, which means you just need the reciprocal up front. All right, more basic integrals. When you integrate 6e to the x, you're really just integrating e to the x and multiplying a 6 afterwards. The integral of e to the x is e to the x, so it should be either b or c. And the integral of 7 over x is really the integral of 7 times dx over x, or in other words, 7 times a derivative over its original expression, which again I told you was the absolute value of x inside of ln. So our answer is C. I'm talking kind of crazy, I know. It's because it's midnight again. And it looks like this will be the last example before I have to pause this, because I can only make 15-minute YouTube videos at a time. All right, up next we're supposed to evaluate the definite integral from -3 to 1. And the idea about this problem is we have to do this in 2 pieces because we're split in this interval into 2 different functions. So the first thing I can do is I can go from -3 to 0, and if I'm doing that, I'm looking at the bottom function. So I'm going to integrate -2x, and what that's going to give me is, again, you can think about just moving the -2 out front, or however you work this out, you're going to end up getting -x squared, evaluated from -3 and 0. And when you do that, you're going to have the negative out front, and you're going to have 0 squared minus -3 squared, lots of negatives going on here, and we end up with negative 0 minus positive 9, so we end up with -9, so we get 9. And then now I have the first half from -3 to 0. I know it doesn't seem like half, but really it kind of is in terms of what you have to do for this problem. And next we can get the other half. In other words, it's going on from 0 to 1, and that means we're going to have to use the top function. Now again, when you integrate this, think about that as x to the 1/2, so first increase the power by 1, offset it by its reciprocal. This time just keep the 9 out front. We kind of seen that before already. Evaluate this from 0 to 1, and 9 times 2/3 is 6, so we have 6 times 1 to the 3/2 minus 0 to the 3/2. And that's really just going to be 6 because this is just 1 and that's just 0, so 1 minus 0 is 1, and 6 times 1 is 6. But we're not done yet because we have to combine the answer to both parts, which gives us 15.